The mevalonic acid pathway. The mevalonic acid pathway is used for the production of terpene hydrocarbons that often have a use as secondary metabolites in plants. The pathway begins with two acetyl-CoA, which bind together using the enzyme acyl-CoA acetyltransferase. The product is acetyl-CoA. This then reacts with another acetyl-CoA in the presence of beta-hydroxy-beta-methyl-glutaric-CoA synthase, forms beta-hydroxy-beta-methyl-glutaryl-CoA. Next, the beta-hydroxy-beta-methyl-glutaryl-CoA reacts with two NADPH and two protons and the enzyme beta-hydroxy-beta-methyl-glutaryl CoA reductase to form mevalonic acid. Mevalonic acid is a 6-carbon hydrocarbon that is not linear. The mevalonic acid is then phosphorylated using ATP with mevalonic acid kinase, followed by ATP with phosphomevalonate kinase. This yields mevalonic acid 5-pyrophosphate. The term pyrophosphate is used when two phosphoruses are adjacent. The mevalonic acid 5-pyrophosphate then becomes the building blocks for terpene synthesis. The mevalonic acid 5-pyrophosphate reacts with ATP and the enzyme diphosphomevalonate decarboxylase to release carbon dioxide and inorganic phosphate and yield isopentyl pyrophosphate. The isopentyl pyrophosphate can be called an isoprene unit. It has 5 carbons with no oxygens and can serve as the basis of other more sophisticated hydrocarbons. The isopentyl pyrophosphate can be isomerized into dimethylallyl pyrophosphate. This reaction is reversible using the same enzyme. These two, the IPP and the DMAPP, then serve as the basis of the formation of terpenes. Rather than trying to write these out with all of the carbons and hydrogens involved, we're going to abbreviate these into line figures. Any bend in the line represents the location of a carbon. The isopentyl pyrophosphate will be represented like this. The dimethylallyl pyrophosphate will be represented like this. One molecule of IPP and one molecule of DMAPP combine to form one molecule of geranyl pyrophosphate. This reaction causes the release of a pyrophosphate molecule. The geranyl pyrophosphate will have 10 carbons. Next, a molecule of IPP will react with the geranyl pyrophosphate to form a molecule of farnesyl pyrophosphate. Farnesyl pyrophosphate will have 15 carbons. The farnesyl pyrophosphate will react with a molecule of IPP to form a molecule of geranyl pyrophosphate with 20 carbons. Each combination will cause the release of a pyrophosphate. Larger molecules will form by the combination of farnesyl pyrophosphate with farnesyl pyrophosphate with 30 carbons, or with the combination of geranyl pyrophosphate with geranyl pyrophosphate with 40 carbons. Terpenes are often basic chemicals that are secondary metabolites of plants.